Assalamu alaikum. Every time you open Gmail, buy something on Amazon, or send a WhatsApp message, your data is locked by an algorithm invented in one sleepless night in 1977. That algorithm is RSA, and the story of how it came to exist is not just a math story. It's a story about a problem that people thought was literally impossible to solve. And I'm going to tell that story in this video. Before the 1970s, if two people wanted to communicate secretly, they had to first meet in person to exchange a secret key or use trusted courier. Spies use code books delivered by trusted couriers. Banks use physical key lists. Armies used cipher machines. The fundamental rule of cryptography was simple and painful. Before you encrypt, you must first secretly share the key. So how could you possibly tell someone a secret over a public channel when a spy is listening to every word? In the early 1970s, a few people started to wonder if that law was actually breakable. The first crack in the old wall came from a graduate student named Ralph Mackel at Berkeley. He had a clever idea. What if you could solve the key exchange problem by making it very expensive for a spy but cheap for the two legitimate parties? Merkel called these puzzles. His paper was submitted around 1974 to 1975. It didn't fully solve the problem, but it planted a very important seed. Maybe you don't need a pre-shared secret at all. This idea reached the ears of two researchers at Stanford, Diffie and Hellman. Whitfield Diffie was an obsessive cryptography enthusiast who spent years thinking about this problem. Martin Hellman was his advisor at Stanford. Together, they published arguably the most important paper in the history of cryptography, New Directions in Cryptography, in November 1976. Their paper proposed the idea of a private key and a corresponding public key, the earliest publicly known work to do so. They claimed for the first time that true strangers can agree on a shared secret key right in front of a spy without ever having met before. How? The trick lives in a beautiful mathematical asymmetry. Some operations are easy to do in one direction, but nearly impossible to reverse. If I tell you that 5 to the power 4 mod 23 is equal to 4, it's easy to calculate. But if I just give you 4 and ask you what was the exponent, with large enough numbers, you would need to try many possibilities. This is called the discrete logarithm problem. Easy to compute forward, hard to reverse. Let's see, how is it useful in reality? I have shown all secret values in red. Let's say Alice and Bob publicly agree on two numbers, a prime number p and a base g, which is a primitive root modulo p. Say p equal to 23 and g equal to 5. These are public. The spy knows them too. Alice chooses a secret integer a is equal to 4, then sends Bob a is equal to 5 to the power 4 mod 23, which is equal to 4. Bob chooses a secret integer b equal to 3, then sends Alice b equal to 5 to the power 3 mod 23, which is equal to 10. Alice then computes her secret key using b, what Bob has sent to her, which is s equal to 10 to the power 4 mod 23 equal to 18, uh, which is the secret key of Alice. Bob computes his secret key using a, what Alice sent to him. So Bob's secret key s is equal to 4 to the power 3 mod 23, which is equal to 18. Both got s equal to 18. That's their shared secret. The spy heard p equal to 23, g equal to 5, a equal to 4, b is equal to 10, but cannot figure out 18, the secret key, without solving the discrete logarithm problem. Why does this work mathematically? Because Alice computes b to the power a mod p, which is equal to s, and Bob computes a to the power b mod p, which is equal to s as well. You get the same result, but the spy, who only sees g to the power a mod p and g to the power b mod p, they cannot combine them to get g to the power ab without knowing a or b, but finding those from the public values is computationally impractical with large numbers. This was magic to strangers, no courier, no pre-shared secret. A shared key appears out of thin air. But here is where the story gets interesting. This is the gap. Let's understand it clearly. Diffie-Hellman solves the key exchange problem. Two people agreeing on a shared symmetric key, but it has two serious limitations. Limitation 1. It only produces a shared key, not a full public key encryption system. Diffie-Hellman gives you a shared secret, but it doesn't directly let Alice encrypt a message to Bob, using only Bob's public information, in such a way that only Bob can decrypt it. That requires something slightly different, a trapdoor one-way function. A function that is easy to compute in one direction, hard to reverse. Limitation 2. No digital signatures. Diffie-Hellman cannot sign a message. If Alice sends Bob a message, Bob has no proof that it came from Alice. Anyone could have sent it. At MIT, three researchers read the Diffie-Hellman paper and got excited. Ron Rivest, Adi Shamir, and Leonard Edelman. They were at MIT, made several attempts over the course of a year to create a function that was hard to invert. Rivest and Shamir, as computer scientists, proposed many potential functions, while Edelman, as a mathematician, was responsible for finding their weaknesses. They tried many approaches, including knapsack-based and permutation polynomials. They kept failing, month after month. Rivest and Shamir would propose a clever function, Edelman would break it. Then they would try again. Then came the night that changed everything. In April 1977, Rivest, unable to sleep, with a math textbook, started thinking about their one-way function, the trapdoor function. He spent the rest of the night formalizing his idea, and he had much of the paper ready by daybreak. The insight Rivest had that night was elegant. Use the difficulty of factoring large numbers as trapdoor. Multiplying two large primes together is easy. Factoring the result back into those primes is extremely hard. That asymmetry is the lock. The two primes are the key. So how is this difficulty become a trapdoor function? What Rivest proposed was like the following. Alice picks two secret prime numbers. P is equal to 61 and Q is equal to 53. Nobody knows this but Alice. These two numbers are the seed of everything. Then multiply them together and we get n equal to p times q equal to 3233. This is the n. It's public to the world. And that's fine because nobody can reverse it back to 261 and 53 without spending more time than the universe has. Now compute lambda n, the Carmichael's torsion function. Think of it like a clock. A normal clock resets every 12 hours. Hour 13 is just 1 hour is just hour 1 again. Lambda n tells you that your mathematical system resets every lambda n steps. That's all it is, a reset point. This matters because when you select E and D around this reset point, applying E then D is like walking exactly one full cycle around the clock. You end up right back where you started. That's why original message always comes back perfectly. To find it, subtract 1 from each prime. Take their LCM. Now we keep lambda n is equal to 780, completely secret, and never share it. Now, pick a number e with one rule. It must share no common factors with lambda n equal to 7, so that e and lambda n are co-prime. That is, their GCD should be equal to 1. So we can pick e is equal to 17, making sure that one rule. Now, n equal to 300, 3233 and e is equal to 17. This is Alice's public key. Anyone in the world can use these two numbers to send a message to you. We need a number d such that d times c equal to 1 mod lambda n. So this equation is asking, what's the value of d? 1 multiplied by 17 gives a remainder of 1 when divided by 780. The answer, d is equal to 413. So n equals 3233, d is equal to 413. This is Alice's private key. Now let's see how Bob communicates with Alice using RSA. Bob wants to send Alice the number 65 secretly. He has Alice's public key, so he sends the encrypted message C, that is equal to 2790, to Alice using his public key. So spy intercepts it, stares at it, but can't do anything with it. Alice receives 2790. He uses his private key to decrypt the message and recover the message m equal to 65 that Bob has sent to him. Original message perfectly recovered. So why does this math work? When e times d leaves remainder 1 after dividing by lambda n, that is Carmichael's total function, something beautiful happens. Applying e then d is the same as going exactly one full cycle and landing right back at the start. The message returns to itself. Think of it like walking around a circular track. The message M starts at the top. E walks you forward some steps. D walks you at the exact remaining steps to complete the full cycle. You end up exactly where you began. That is your recovered message. So why not Spy could decrypt the original message? Spy sees N equal N and E. To break in, she needs D. To find D, she needs lambda n. To find lambda n, she needs P and Q. To find P and Q, she must factor n. With real RSA, n is a 600-digit huge number. No computer on Earth, not even all computers combined, can factor that before the sun burns out. Diffie-Hellman had two open problems. RSA solved both with the same mechanism. How? Alice writes a message. She signs the message with her own private key before sending it. This is how Bob can recognize that Alice has sent this message. It solved Diffie-Hellman limitation 2 that we showed before. Alice then encrypts with Bob's public key. When Bob receives it, he verifies the signature using Alice's public key and decrypts it with his own private key. Nobody else holds her private key, so it basically solved Diffie-Hellman limitation 1. Two limitations, one algorithm, both closed. There is a twist in this history. An equivalent system was developed secretly by English mathematician Clifford Cox in 1973 at Government Communication Headquarters, that is the British Signals Intelligence Agency. That system was declassified in 1997. Cox independently invented the same algorithm 4 years before Rivest Sleepless Night, but it was classified top secret and locked away. The world didn't know. So that's all. Hope you enjoyed the video.